All right, guys, we have one more thing we need to discuss in terms of titrations before we start working through some problems, and that is our titration curves, are also called pH curves. This is a very common and important tool for analysis of titrations. So what I want us to recognize is we've got 4 graphs that we're going to be looking at right here, and I have another set of 4 on the other slide we're going to look at as well, and then we're going to actually create our own. Is that there are different types of titration curves, and what I want you to recognize, this one is a strong acid, strong base. This one is a strong acid, weak base. This one is a weak acid, strong base. And in reality, we're never really going to do a weak acid, weak base, because if you can't tell, that line just looks pitiful and sad. And I'll scroll down so you can see it. That's not something we will do on the AP level. But I want to talk about the strong acid, strong base. So first off, notice where we're starting. We're starting with our pH very, very high. What does that tell us? That tells us we're starting with a strong base. And what actually is going on here is if we think of our flask, and I know that's a pitiful drawing, and we have our burette, and our burette is dropping into our flask, our pH meter is in whatever is down here in the flask. So what that means is we're starting with a strong base, and we are adding the strong acid into our strong base. Now notice what's happening is our pH is changing very, very slowly here, and that's just because of the nature of that strong base. And then all of a sudden we have this huge plummet. This plummet is called our equivalence point. This is what we've talked about before. This is when the moles of the acid equal the moles of the base. And something we can get from this line is about halfway through this straight line, whether it's a weak acid, strong base, whatever type of pH curve is, if we can find that straight line and take it over, the pH at the equivalence point can be found by about halfway through this straight line. And of course, as we keep going past the equivalence point, meaning we have more acid than we do base, we end up with that same type of curve we saw up here, except just in the acid spectrum. A couple points again, our equivalence point is found, we can find our equivalence volume, if you will, by just taking it straight down and looking at our X value. Our Y value, the middle of this straight line, tells us the pH at our equivalence point. And we can also get some other information specifically when we have weak acids and weak bases, which we'll look at in just a moment. But again, one of the things we want here is this equivalence point we want to be our endpoint. So what we can do is look at the pKa of our indicator, because our indicators usually are weak acids or weak bases. And our pKa of our indicator should match around the same range as the pH at our equivalence point. Okay? So that's kind of some of the stuff we can get from this information. So let's look at our strong acid, weak base. Notice here, we're still starting in our base spectrum. So that means we're still starting with our base in our flask and we're adding the acid to it. Notice here though, our curve looks very different than it does up here. Up here, we actually have this kind of nice, I know it's pixelated, but this very nice gradual curve. Here we kind of have this weird little swoop, if you will. That is because when we have a weak base reacting with a strong acid, okay, so let's just say we have NH3 reacting with HCl, it's going to form the ammonium ion and the chlorine ion. Because as we're adding HCl, we still have some base and we have some conjugate forming, we end up with a buffer forming. And this is that buffer region curve that we see. When it's just a strong acid or a strong base, we don't see that, we see more of a gradual change, not this kind of weird swoopy change. Okay, so still same idea that we can get information from. So we find that straight line, a little bit shorter of a straight line here because again we have a little bit more dynamic change in pH here in this buffer region versus this gradual change. And again, that's just dealing with that buffer relationship between our concentration of our weak acid and conjugate, or in this case, our weak base and our conjugate. But we find that straight line and we can take it straight down. And that would still give us our equivalence point, volume at our equivalence point. And if we find our middle point of that straight line and take it over, we can get the pH at the equivalence point. Now notice our pH here is less than 7. It's 7 over here for a strong acid, strong base, but it's less than 7 for a strong acid, weak base. Well, why? Over here, let's say we have HCl and sodium hydroxide. That's going to form sodium chloride once both of our base and acid have reacted completely. Well, if we think back to our salt, sodium chloride's not really going to interact with water, so our pH is going to remain 7. It's just going to be water. Over here, because once all of our base and all of our acid reacts, we are left with this ammonium ion and the chlorine ion, which does nothing. That ammonium ion is going to be reacting with water to produce, that should be water, not hydronium, sorry. I'm getting ahead of myself. There we go, water. To produce the hydronium ion, and again, the ammonia ion. And because we have hydronium being produced, we're going to end up with a acidic solution. It's going to be below 7. And again, the idea behind this is we want our pKa of our indicator, not of the acid, not of the base, but the indicator, to be around this pH range, so our endpoint and equivalence point end up being the same point. Now, let's talk about pKa and pKb of our weak acid or our weak base. In this case, weak base, so we're going to talk about our pKb. And I wrote A. I said B, wrote A. There we go. So this is the negative log of our Kb. We can actually find this very readily by finding the half equivalence point. So remember, our equivalence point is when the 2 moles of the acid and base are equal. Half equivalence point is halfway there. So if this is our volume at the equivalence point, half of that volume is our half equivalence point, halfway point, midway point, whatever you want to call it. Well, the pH right there equals our pKb. And the reason being is it goes back to that Henderson-Hasselbalch equation where pKa equals pH minus the log, or plus the log, whatever it is, of the conjugate over the HA. Well, if we remember at the half equivalence point, half of this has reacted, all of this has reacted, which means this guy and this guy are equal. And you can go back and look at the math if you want to kind of prove that point, which means this ratio is 1 and the log of 1 is 0. So pH equals pKa. That's also true for pKb as well, equals pH. In this regard, actually it equals pOH, but then we can find pH from there. So that's one of those important things that we can get from this information as well. So if I'm looking at this guy down here, weak acid, strong base, same idea. Strong base, we see that very pretty gradual. I know it's pixelated with the picture, but that's okay. And then down here, we don't see quite that same gradual. We see more, a little bit of that swoop. It's not quite as dynamic here. But we draw our straight line, we take it over, and notice our pH is above 7. Why? Well, once our weak acid reacts, we're left with the conjugate base. It reacts with water to form hydroxide ions, and that formation of hydroxide ion gives us a pH above 7. Okay, so fantastic. And again, we can find that half equivalence point and work on it from there, okay, to find our pKb, pKa, whatever it happens to be. And again, we're really never going to play with the weak acid, weak base, because that gets all sorts of messy. Here's just another version, okay, so notice here we have a weak acid, strong base, and it is a whole lot easier to find the equivalence point and half equivalence point when we actually have pretty numbers. So we have our equivalence point. We can take it down, find whatever that volume is. Half of that volume is our half equivalence point. Find the pH there, and they already gave it to us, and I know it's really blurry, but pKa equals 4 because our pH is 4 at this point in time, which means our Ka value is 1 times 10 to the negative 4th, or thereabout. And that allows us to kind of see how strong or weak that acid actually is. And again, we know it's not a strong acid, but how strong of a weak acid is it? Okay, so that's kind of what we have with our pH curve. So again, here's kind of a strong acid, strong base. We see that same idea. Again, we're not going to deal with weak acid, weak bases just because we're not going there. And we'll talk about multiples. Actually, we really won't talk about multiples, but just so you have an idea, if I do have a polyprotic acid, this one's really messy because it's a weak acid, weak base. Essentially, what would happen is I would have multiple equivalence points that would be occurring, multiple of those straight lines, if I can make that a little bit clearer. Because each hydrogen would have an equivalence point with the added base, or vice versa if it was a weak base. Okay? So far, so good. All right, just very quickly, if I was to ask you to create a titration curve, the first thing you would need to do is to find your pHs at all of these points. So I'm going to let you do that real quick. Okay, so I basically went through and calculated my concentration of the 0.1 molar hydrocyanic acid. I changed B instead of just a random point in the middle. I turned it to my half equivalence point, so 25 milliliters. You're welcome to pause again, recalculate, and see if you get the same thing I do. And then, of course, we have our equivalence point. So from there, all we're going to do is put this into a pH curve. Okay, so pH curve is simply going to be volume on the bottom. And usually this is the volume of the species added, so this would be the sodium hydroxide added. And then we have our pH. So before any hydroxide is added, okay, so at 0, our pH is, call this 7. It is around 5.10, so we'll put it right here as our starting point. Okay, from there, our equivalence point is at 50 milliliters, so we'll put that here. Our half equivalence point is at 25 milliliters. Okay, at our equivalence point, we have a pH. We'll do this. We'll do 5, 9, 11, 13, and then we can kind of keep going down at 3 and 1. So we're starting at 5. Okay. From there, at our half equivalence point, we end up at around 9. Okay, and then at our actual equivalence point, we end up at around 11. Okay, so we'll put that up here. So what does this actually look like? And this is a little bit of an odd one to draw, but that's okay. So just so you can kind of see it, we have our slow little swoop kind of up to there, and then we would have a big jump. Okay, let's see if I can make that a little bit cleaner. Not really. Like I said, this one's a little bit hard to draw just because the pH jump is a little bit wonky here. And that's just because of the nature of cyanic acid. Put that there. Let's see if maybe we can draw it a little better. Something along the lines of that, which of course this would be a little bit cleaner. And then of course as we added more hydroxide, we'd have the curve up there. So this one's an odd one, but that's okay. So you'll have a couple practice problems from here that you can work on, and the videos to watch those to kind of see how you do, and you'll have some pH curves to work through as well. Thanks, guys.